Integrated 3, 10-125, Josephina thinks that she has discovered a new pattern, shown it right. Check her equations by multiplying. Does her pattern work? So to check by multiplying, you would multiply the quotient times the divisor and you'd get the dividend. Like, does x minus 1 times 1 equal x to the 1? It does. Does x minus 1 times x plus 1 equal x squared minus 1? It does, because it's a difference of squares. And then you could check this one by multiplying this times this to see if you get this. I did something else to prove that her pattern works. What I did is I noticed that was a difference of squares, so I just did some canceling just to make sure the thing worked. And that's difference of cubes, so I did my canceling. It worked. So that's her pattern, and I noticed a couple things about the pattern. I noticed that this term is just this term with an x added on to the left-hand side. See, like this, it's like it got a x squared added on to the front of it. This one got an x cubed added on to the front of it. So, and I also noticed that the first term is one less. Like this is x cubed minus 1. That's x starts with the x squared, and they go in descending order, like x to the 2, x to the 1, x to the 0, x to the 3, x to the 2, x to the 1, x to the 0. So I'm convinced that her pattern works. I've checked it by multiplying and by doing some factoring. So the answer is yes to letter A. Letter B says, based on her pattern, what would x to the 5th minus 1 equal? And is it true? And justify your answer. So if I just keep following her pattern, I see that x to the 3rd, it starts with the x squared, and then it just goes down in descending order of exponent, of degree. And so x to the 4th, that would be x cubed. So x to the 5th would start with x to the 4th, and then x to the 3rd, and then x squared, then x, and then 1. And I actually did the long multiplication just to check it. So if this started out as being x to the 5th minus 1 all over x minus 1, and that all equaled that, then what I can do is I can multiply that times, this is the quotient, and I can multiply it by the divisor and get the dividend back again. So that's what I did here. See, this one right here is across the top of my area model box, and this one is the divisor. Or well, anyway, I'm multiplying these together just to make sure I get the quotient. So x to the 4th times x, that's x cubed. As I did this, I noticed like I got the negative x to the 4th, and then up here I got an x to the 4th, and I kept getting these cancellations. Everything canceled out. They're all canceling out. And I end up with x to the 5th minus 1. So that's my way of justifying that the pattern works, and that the next thing would be, this would be the next item in the pattern. And then letter C says, make a conjecture about how to represent the result for x to the n minus 1 over x minus 1. You'll need a dot, dot, dot in the middle of your expression. So the answer key I disagree with, because it says we're going to start with x to the n, and that's not what I see in my pattern. In my pattern, I see if it's x squared, I just start with x to the 1. If it's x cubed, I start with x squared. It's always one less. If I have x to the 4th minus 1 in the numerator, I'm going to start with x cubed. X to the 5th starts with x to the 4th. So x to the n would start with x to the n minus 1. So I think there's a problem with your answer key. And then this one would be one less. So if you minus n minus 2 is 1 less than n minus 1. And it would keep going 1 less, 1 less, 1 less. And then, like, this one right here would be x squared, x to the 1, and just 1. And that's it.